students. In this video, we are going to learning about applications of Bernoullis principle. In the previous class, we are discussing Bernoullis principle. What is the Bernoullis principle? Bernoullis studies on fluids. It has given a statement. What is the statement? The sum of potential energy, kinetic energy, and pressure energy per unit mass, which is remains the same. Actually, this is applicable to only for ideal fluid. So, in the previous class, we discussed the ideal fluid. Ideal fluid has four characters, which are first one is streamline flow. That means velocity of all the particles, all the water molecules same throughout the path. Second one is the fluid must have incompressible. That means density remains the same of the fluid. Third one is which is irrotational. Net angular momentum of the fluid is 0. There is no net angular momentum. That means remains constant. And fourth one is non-viscous fluid. There is a viscous force acting between the adjacent layers. So this force must be 0. Such fluid is considered as ideal fluid. So Bernoullis is applying this principle for ideal fluid. Okay, once just recall the Bernoullis principle, then we are going to applications. So this is a non-uniform cross-section of a tube, which is a non-uniform cross-section. There is a non-uniform cross-section. Okay, this I'm taking as the area of cross-section at this end A1 and at this end A2. This is at a height of, how much height is it? And is this end is at a height of H1. This end is at a height of H2. So these are the two ends. Okay. Here the fluid is entered with the velocity v1, and then at this end it is leaving at this velocity v2. Okay. This end has end is taken as P. This end taken as Q. Okay. So the fluid is entered into this tube. So here at this end, so the sum of potential energy and kinetic energy and pressure energy per unit volume, which is remains same. And at this end, so here also the sum of pressure energy and potential energy and kinetic energy per unit mass of the fluid is remains same. That means at this end and at this end, so the total energy is remains constant. This is the Bernoullis principle statement. So once again, we will take it here. So here at this end, sum of the potential energy is means I'm taking per unit mass. So I'm taking as G H1 plus kinetic energy per unit mass. I'm taking half E1 square plus pressure energy per unit mass. I'm taking P1 by rho. So at this end, so this I'm taking as G H2 plus I'm taking as this is potential energy. Now at this end I'm taking as it's kinetic energy per unit mass. And the pressure energy I'm taking as okay. So these are remains constant. This is the Bernoullis principle. First application of Bernoullis principle is the speed of Efflux. So on this torsionally, a scientist torsionally works on given this principle. So this is also called as the Bernoullis principle. So speed of Efflux. What is the speed of Efflux? Okay, we are going to discuss here. So I am considering a water tank. This is like as a water tank, which is on a flat surface. This is taken as a surface. This water tank is filled. Air for this water tank is like air cross section of this water tank. I am taking as E. So this water tank is filled with liquid, which is initially attached position. So this is taken as fluid. The area of this cross section is A. The height of the fluid is taken as H. This is the water level, the fluid level. So the fluid is initially at rest position. Its potential energy is okay, mgh. Okay. So the top surface of this fluid is exposed to atmosphere. This atmosphere is acting on this fluid top surface. Okay. Now I'm taking it. I'm making a small hole. Okay, this called as orifice. Okay, I'm taking as an orifice. it means a small hole making at its bottom. Okay, the level of this orifice is taken as from this liquid surface, I'm taking as a small h, I'm taking here. Then what's happening here? The liquid is coming out, the fluid is coming out like this. It is reaching the ground. That means it is reached. So here the fluid is coming with a speed, what speed which is coming out from this orifice, that is called as the speed of efflux. Speed of efflux. The speed with which it comes out from the tank from a small orifice, a small hole. This is called as speed of efflux. So we should find out with what speed which is coming out. We should find out by using this Bernoullis principle. Okay, by using this Bernoullis principle. So here I am taking two surfaces. One surface is at top and the other is that I am taking as and its orifice. Okay, this orifice, this liquid is coming out from the tank, which is also exposed to atmospheric pressure. So at this top surface, atmospheric pressure, at this top liquid coming out at this atmospheric pressure is same only. Okay, now I am taking applying the Bernoullis principle. Okay, I am taking as at the top. I'm taking at top of fluid. I'm applying top of fluid. Okay, so at top of fluid is the pressure I'm taking as P1 equal to atmospheric pressure. And I'm taking as initially it's the velocity I'm taking as V1 equal to which is 0, and which has height is I'm taking as I'm taking H1 equal to as capital H. H1 is sorry I'm taking from here to this surface I'm taking as small h. Okay, at the top of the fluid. Next I'm taking at the bottom. And I'm taking as a bottom. I'm taking as a bottom of fluid. Okay, at the bottom. The main orifice. I'm taking as an orifice. Okay. So here at orifice, I'm taking pressure is applied as this is also exposed to atmospheric pressure. So I'm taking PT equal as a PVA. I'm taking PT equal to. So I'm taking as a V to velocity. So here the fluid is coming out from this tank with the speed how much here? I'm taking as V. So I'm taking as a V. So here H2 I'm taking H2 equal to. So from this orifice to this fluid is how much height level? H height level. This height initial height. Then at this I'm taking as a reference point. So the height of this orifice, how much is this? I'm taking as a 0. Height is 0. So this is the given data. So this we can apply to Bernoullis principle. Okay. So then we can find out Bernoullis principle. Speed of efflux. So I'm taking at the top applying Bernoullis principle how much here? Okay, for real mass I'm taking here G into H1 plus potential energy per unit mass. I'm taking kinetic energy per unit mass P1 square pressure energy per unit mass. Okay, which is equal to at this orifice. So potential energy per unit mass plus kinetic energy per unit mass plus I'm taking as pressure energy per unit mass I'm taking. Okay, so I'm taking here pressure energy, potential energy. How much here? G W as H plus half velocity is 0. I'm taking 0 square plus pressure is I'm taking as PA by as which is equal to at this height how much here? 0. G W which is 0 plus half V2 means which is coming out the speed V square plus pressure is P2 is means PA by rho. Okay, so from that we can take this equation. Not coming here, check it here. So GH plus I'm taking as 0. This PA by rho cancel. This value is cancelled. Just you can take it GH. Okay, which is equal to this term is 0. Then you can take it half. I'm taking as V square. So find the V square value. So I'm taking V square equal to 2GH. So V equal to root over 2GH. This is the speed of efflux. This is the speed of efflux. With this speed, which is coming out from this tank. Okay, speed of efflux, which is root over 2GH. Here, it is very clear. This speed of efflux is independent on the fluid, whatever the fluid it has. the quantity of the fluid. Maybe up to this level, up to this level, up to this level, whatever the fluid, okay, which is that means whatever the quantity which is independent of the quantity of the fluid and nature of the fluid and the orifice, area of the orifice, whatever the area, okay, which is maybe smaller, maybe which is more, whatever it is. Speed is independent. This speed of efflux is independent on nature of the quantity of fluid and height of the it's which one? This is area of the orifice, which is independent, which depends on only height of the fluid from the orifice, from the surface to orifice. How much height is there, which it depends on, and depends on acceleration due to gravity. This is the speed of efflux. Speed of efflux. Next, we are going to discussing how much time taken this fluid is reaching the ground. How much time taken to find out. Okay, the time taken by the fluid to reach from this level to this orifice, how much time taken we should find out. Okay, further I'm taking here this is remaining height is I'm taking as this height is capital H minus I'm taking as a small h, this height I'm taking as. Okay, so we can use it S equal to I'm taking ut plus I'm taking as half I'm taking as ut square. Okay, so x means how much height from this surface ground, this orifice, how much height is there. So I'm taking as h capital minus small h, which is equal to. Initially, the fluid has a rest position. Initially, rest of the fluid I'm taking as rest position equal to 0. I'm taking half a means I'm taking this square. So h minus small h is equal to I'm taking as half g square. So find this value here. 2h minus small h by I'm taking g, which is equal to this square. That implies here t equal to root over 2 into h minus small h by g. This is the time taken. This is the time taken by the fluid to from this top level to reach this orifice up to this level, up to empty this level. The time taken. This is the time taken. Okay. Next one. Okay. The fluid is reaching the ground. This is called as a range. So horizontal range. What is the range? You should find out this also. Okay. So to find the range of this fluid entering the ground, reaching the ground, that is from the bottom of the tank. We should find out. So from that, for that we can find out the range is equal to that as velocity into velocity that as time. Velocity into time I'm taking here. So velocity is how much coming here? That is velocity is root over 2g small h into time that is root over 2 into capital H minus small h by and that as small g. So together take here root over I'm taking 2 gh into I'm taking 2 capital H minus small h by I'm taking as a g. Okay, so here g can cancel here. This 2 into 4. This 4 is coming from the root. This value is I'm taking as 2. That implies I'm taking as r equal to this 4 is coming root outside 2 into root over h into capital H minus small h. This is the range. Okay, this is the range. Okay, once again we can recall it here. So velocity of the speed, this speed of efflux is v equal to, okay, how much coming here? You can check it here. So v equal to root over 2gh and the time taken, that is to reach the top for bottom of this orifice, how much time taken? T equal to root over 2 into capital H minus small h by and that has g and the range. Range means this is the value. Okay, so this is the time of, this is speed of efflux.